In May 2018, GDPR came into force across Europe. Every company that stored personal data about European citizens had to comply with one of its core requirements. If a user asked to be forgotten, their data had to be deleted. A mid-sized e-commerce company had prepared for this. They added a column to their users table called deleted. When a user submitted a deletion request, the column was set to true. A nightly job scanned for deleted users and purged their personal data. 6 months after GDPR came into force, a regulator's audit found personal data still present in the system for users who had submitted deletion requests. The engineering team investigated. The deleted column was working correctly. The nightly job was running correctly. The personal data was being purged correctly. For every user where deleted was true. The problem was the users where deleted was null. These were accounts created during a system migration, 2 years before GDPR. The deleted column didn't exist yet when they were created. When the column was added, existing rows received no default value. Their deleted column contained null, not false, not true, but unknown. The nightly job filtered for users where deleted equals true and purged them. It filtered for users where deleted equals false and kept them. It never asked what to do with null. Null is neither true nor false. The condition deleted true doesn't match null. The condition deleted false doesn't match null either. Null users fell through every filter. They were never purged. The company had complied with the letter of its own implementation. It had not complied with GDPR. The personal data of an unknown number of users who had requested deletion was still sitting in the database. The fine was significant. The remediation cost more, and the root cause was a boolean column that was never true or false. It was 3 values: true, false, and unknown. This is the boolean trap. Most people think of a true-false column as the simplest possible data type. 2 states: binary, unambiguous. In SQL databases, a boolean column is not binary, it is ternary. It has 3 possible values: true, false, and null. And null, as we have seen before in this series, does not behave like false. It behaves like unknown. A third state that most Boolean logic was never designed to handle. The SQL expression deleted false returns true for rows where deleted is false. It returns false for rows where deleted is true. It returns null, neither true nor false for rows where deleted is null. And rows where the condition returns null are silently excluded from results. Not included, not rejected with an error. Silently excluded. This is not a bug in SQL. It is how SQL was designed to handle uncertainty. The problem is that most developers write Boolean conditions assuming 2 states and deploy them into a system that has 3. The null case is the most dangerous manifestation of the Boolean trap, but it isn't the only one. The second problem is interpretation drift. A Boolean column called active means something when it is created. Active means the account is in good standing and can place orders. 6 months later, a developer adds a feature, account suspension. Suspended accounts shouldn't be able to place orders. They set active to false for suspended accounts. A year later, another developer adds a feature, trial accounts. Trial accounts can place orders but with restrictions. What do they set active to? True, because trial accounts can order. But now active is conflating 2 different concepts. Can this account place an order? And is this account fully paid? 2 years later, the permissions system reads active and makes access decisions based on it. The permissions developer assumes active means fully paid. Trial accounts, which are active but not paid, receive paid tier permissions. The column never changed. The meaning accumulated interpretations until it meant several things simultaneously, and none of them cleanly. The third problem is the negative Boolean. A column called deleted, or disabled, or blocked, or is spam, encodes its meaning as the presence of a negative state. This creates a subtle but important asymmetry. When you query for active records, you write where deleted false or where deleted is not true. Both conditions exclude NULL, records that have never been explicitly marked as not deleted, perhaps because they predate the column, are invisible to the query. This is not a theoretical problem. It is the exact failure that caused the GDPR compliance breach. The records that needed to be purged were the ones that had never been explicitly set to anything. The column's absence of a value was indistinguishable from an absence of a deletion request. A negative boolean requires explicit handling of NULL every single time it is queried. Most code doesn't do this. Most code was written by a developer who assumed that a boolean column had two states and wrote conditions accordingly. So how do you design boolean columns safely? The first rule is to set a default value on every boolean column. When the column is created, decide what is the default state. For a deleted column, the default is false. Records are not deleted unless explicitly marked. For an active column, the default is true. Accounts are active unless explicitly deactivated. Setting a default eliminates the null case for new records. For existing records in a migration, run an explicit update to set every null to the appropriate default before the column goes into production. Never allow a boolean column to contain null if your business logic treats it as a two-state value. The second rule is to use I is true and I is not true, rather than equals comparisons. Where deleted is not true returns every row where deleted is false, and every row where deleted is null. It treats both non-true states as equivalent. If your intent is give me everything that hasn't been explicitly deleted, this is the correct expression. Where deleted false is not, it silently excludes the null rows you may need to handle. The third rule is to split overloaded booleans into explicit status columns. When a boolean column has accumulated multiple interpretations, when active means both can order and is paid, replace it with a status column that names each state explicitly. Account state, with values active, trial, suspended, closed, is unambiguous in a way that a boolean never can be, once the business has more than two meaningful states. The fourth rule is to treat boolean columns in migration scripts with the same care as any other schema change. When a new boolean column is added to an existing table, every existing row receives null, unless a default is specified. A migration that adds a boolean column without a default is a migration that introduces a third state into what the application believes is a two-state system. That third state will eventually fall through a filter. The question is only when. Booleans feel like the simplest possible data design: two values, a switch, on or off. But in a database that has been running for years, a boolean column carries the full weight of every assumption ever made about what true and false mean, every state the business has added that didn't fit cleanly into either, and every row that predates the column and received neither value. True and false are not a complete vocabulary for the complexity of real systems. They are a starting point that requires explicit design to stay honest as the system and the business grow around it. The column called deleted that caused a GDPR compliance failures was set to true correctly for every user who requested deletion after it was created. It was never set to anything for the users who needed it most, the ones who had been in the system longest, who had the most data stored, and who had no value in a column that the nightly job was not written to notice. True and false were handled correctly. Unknown was not handled at all, and unknown, in a compliance context, is the most expensive state of all.